element method is a technical approach that is very suitable to face field problems.
Sorry, teacher, can you record the lesson?
Sorry?
Can you record the lesson?
Not sure I know how to do that. Does anyone know?
I think on the 3 points there is a start recording or something like that.
Okay, yeah, got it. Should be this one. Work? Yeah, it says that there is the recording in progress. Okay, so I think I can go ahead. So as I said, finite element method is very suitable to face field problems. So what are field problems? Actually, a field problem is that if you have a given system, so whatever is the shape of it, so a system or a volume with, let's say, defined properties, and you have boundary conditions, so you have your system with boundary conditions, well, you can find the spatial distribution of one or more dependent variables of this system. So this is, for example, the case of displacement, stresses, strains, mechanically speaking, or temperature if you have problems about heat transfer, or the distribution of electric charge, or maybe magnetic field. So these are the kind of examples that we can define field problems. So once you have your model defined like this, and you have your boundary conditions, you have two possibilities to face these problems. One is from an analytical point of view, so you can solve it analytically with an exact solution, or you can face the problem with a numerical approach, so with an approximated solution. So in the case of an analytic approach, you have the exact solution. Or you have the numerical approach. It is going to give you an approximation, so an approximated solution. Okay. In the first case, if you are approaching the problem with an analytic exact solution, what you are going to do is to divide your system into infinitesimal elements. Okay? So in this case, you have infinitesimal elements. And you can use partial differential equations to approach the solution. An example of this approach is when you have to deal with the mechanics of materials. On the other side, you have the numerical approach, where you must divide your structure in discrete and finite elements. Okay, and this is exactly the case, and this is why it is called like this, of the finite element analysis or finite element method. This second part is exactly what we are going to see in detail during this course. At the very beginning, we are also dealing with some examples to demonstrate how we can approach simple cases, both with an analytic method and a numerical method, also to underline what is the difference between the two approaches and to see how a numerical approach that can deal with a very high number of finite elements is going to approximate very well the case of the analytic and exact case. Okay? So let's start with a very simple example, just to deal, to give an example of this approximation. So let's consider the case where we have a real system like this, and you have a force applied at the very tip of the structure. This is the real physical system. Okay, this is the real one. You can approach the problem with an analytical model, of course, by approximating this, let's say, complex structure with a simplified one, losing, of course, some of the features, but still maintaining maybe some of the features that you are more interested in. So, to approach the problem with the analytical method, of course, the degree of simplification should be quite high, but maybe, again, you can maintain the validity of your method if the main features are maintained. So, you can approach the problem like this, so with a mathematical model. And then, or in alternative, you can also approach the problem with the finite element method. So you have again fixed support, and then you can have let's say the structure that is very much simplified but defined with finite elements like this. Or alternatively, if you can also, or if you would like to simplify even more the approach, you can also reduce the dimensionality of the problem by using a monodimensional model like this. So, of course, it should be already clear that the first step is already a simplification of with respect to the reality, and you can find an exact solution of that. In this case, you have a mathematical model that you can rely on. In the third step, that is the discretized. The discrete case. You have a number of elements that are representing your structure, a sort of cantilever beam in this case. And of course, the more elements you're using, the closer to the mathematical model you are, right? So if you, for example, consider so let's say infinite number of discrete elements, of course you are going to the mathematical model with an exact solution. This first step that usually you have to deal with is a validation step. So this is the part that you have to deal with, in the sense that you have the responsibility in a way that this simplification, in a mathematical model is representing the reality or the main characteristics that you want to deal with. Okay, so for example, in making this step, you have to, you have to be aware and you have to accept the simplification that you are not considering, for example, these features here, and also these features that is, let's say, may be an important feature, but negligible for your application. So this is up to you to understand if the physics that is considered in this simplification step is acceptable or not. This other step, that is from the mathematical simplification to the discrete case, is the verification step. And this is the step where you have to guarantee that the physics that is behind, so the kind of equations that are used to solve the problem, are the right ones, so from a physical point of view. The good news is that this step is usually guaranteed by the software itself. So if you are going to represent the structure like this, so the simplified one, the second, with a number of elements, so with a discretization like this, or even with a discretization like this, the kind of physics that you are using and the equations that are used to solve the problem are guaranteed, so the correctness of the equations is guaranteed by the software itself. So you have to deal only with this very first step. So the fact that what you are representing is already a step, there is already a step of simplification in this part. So, of course, this kind of tools is worldwide used in many industries, in many companies. It is a very powerful tool, as you, I don't know if you already have experience on this kind of software, but of course, as you can understand, this step that is up to the user is also a sort of trick. So it's on the base of the experience of the user, of the person that is using the FEM, the FEM, that is really making the result reliable or not. Okay? So this may be a very powerful tool, but of course it should be used carefully and with the good skills. So, questions? Okay, so let's go ahead. Oh, maybe I don't take it. I will then translate. Any questions from who is connected from outside? You still there?
Yes, I have a question. Can you hear me?
Yes.
So, in the numerical approach, the first step is the math model, and then the finite element discretization, and it's a different process from the analytical approach you talked before.
Well, the point is that once you have your model, your first step, your simplification, you can actually, if the geometry is simple enough, of course you can already approach the problem with an analytical approach with an exact solution. That is maybe also the case that I made. So it was a very simple case. So you can also approach that one with an exact solution. But in the most of the cases, also the model that you actually imported in your software, or the simplification that you can make from the reality, is too complex to be faced with an analytical approach. And in that case, you need a finite element method that is going to discretize, to divide your model into very small but finite in dimension elements that can be faced with a numerical approach.
Okay, so the math model is the first step for both of the approach, and then I can choose which one according to the to the problem itself?
Exactly. In fact, now we are, well, the example that I did is quite simple because we have a sort of cantilever beam. And we are going to see many examples that are simple as well. In particular, in a while, we are going to see the case of a bar, actually, that is uniformly tapered. And you will see that we can face that problem both from an analytical and a finite element method point of view. And in this case, we will see that the two solutions are quite similar, especially if we consider a lot of elements in the finite element method. The point is that you don't have the possibility to apply directly an analytical solution to the problem that you will deal with, because the complexity of the structure may be too high to be faced with an analytical approach.
Okay, thank you very much.
Welcome.
Professor?
Yeah.
For example, for finance, can you hear me?
Yes, I can. Go ahead.
For example, for the case of finite element model, the simplification step was quite short. But for example, if we chose to make it more fine, the simplified model will resemble the original model. Am I right?
Sorry, I didn't get the first part of the question.
My mix is working not quite well. Can I write it?
Yeah, sure, of course. You can write it in the chat window. And maybe I can go ahead and then we go back to your question when, in a while, when it is ready, okay?
Yes, sure.
Okay, great. Okay, so as I anticipated, let's start to see very simple examples of how we can use this powerful tool. And of course, we are not going to deal, at least in this part, to very high complexity problem. Then this is just to understand what is the basic concept that is underlying the method. Then, of course, we have ANSYS to make much more complex calculations and models. But it's important that you gain some basic experience on this to understand what is the, let's say, the mechanism that is behind the interface, right? So you have to understand what is, for example, the messages, all the output that the software is going to give you. Because, for who is not very familiar with this kind of softwares, there is the understanding that the FEM, software like this, can really solve everything. So it's a sort of panacea of all the problems. But actually, it is important. The difference between a very good model that can give you the good result and indications for designing a device, and the difference between a good one is on the user, because the user is able to understand, to set properly the input, understand what is giving in output the software. This is the very important part, because also not very skillful people can use ANSYS, but only very skilled users can really understand if the output that is going to be given by the software is correct and it is helpful for a design phase. So I think I have some problems with the connection, but I hope it is still enough for the course. I connected by cable, so I hope. Can you hear me well from Teams?
Yes, we can hear you.
Okay, now I received a message of bad quality of network, but now it disappeared, so I hope it is only for a while. Okay, so let's start to see a very simple example. Maybe. Okay. Okay, so let's see the first example about a 1D bar element. So in this case, we have an element like this that is defined by two nodes, 1 and 2 in this case, and have stiffness k. Node 1 can move on the x direction, and u1 is the displacement that it can perform, and u2 is the displacement associated to node 2. In the most general case, we can also consider a force that is applied on node 1 and another force that is applied on node 2. F1 and F2 are the nodal forces applied to the element. U1 and U2, I'm repeating, are the displacements associated to node 1 and node 2. So we can study this problem by studying the equilibrium node by node. Okay, so if we decompose the problem into, looking at the two nodes, we have F1, this applied to node 1, with the displacement U1, and then there is the force, that is actually the force that is connected the two parts related to node 1 and node 2. The force that is, this force that I'm considering here, of course, is the force related to the spring, so the K, the stiffness K that I used for the element. So for us, F is equal to, for sure you all know, the Hooke's law, in which we can define what is the force associated to this, this internal force. So F, that is the force that node 1 is subject to on the right side, is K multiplied by U2 minus U1. That is U2 and U1, I will repeat, is the displacement of node 1 and displacement of node 2. The other side, for node 2, we have always this force, it is actually the same force, of course, and node 2, where again there is the displacement U2 and the force, F2. So now we can write the equilibriums of the two subsystems, so that on the left, so in this one, we have F1 plus K multiplied by U2 minus U1 equal to 0, right? I'm just making the equilibrium of this first part of the subsystem, where we have F1 and F that we defined as K multiplied by U2 minus U1. Of course, their sum should be 0 to be in equilibrium. The second part, this other part, similarly, we have F2. In this case, is minus because they have opposite direction. K multiplied by U2 minus U1, again equal to 0 for the equilibrium. So we have this system. We can write it also in matrix form, so more compact. We have K minus K minus K, K, which multiplies U1 and U2. That gives you F1 and F2. Okay, we can also write this this system in more compact way. This is something that we will recall several times as matrix K multiplied by the vector D is equal to minus R. So, what are these guys? So, as I said, K, no, I didn't say it. K is the element stiffness matrix. It's defined like this. So, K is the element stiffness matrix. D is called vector of nodal degrees of freedom. Let's move this away. Okay. And R are the loads due to the element deformation. So what is the difference between F1 and F2 and R, and why I added this minus here? Well, actually, we have that F1, F2 transposed is equal to minus R. This is what I did, right? And why we can do that? Because actually this vector is the vector describing the force that are applied to the element. So this is to the element. R, instead, is the force that is, in a way, experienced by an element that is connected to the structure nodes. And that's why there is this minus instead. I mean, that is defined by this minus. Okay, so that's why this equation also holds. Questions? Yes. Degrees of freedom. It's an acronym. Yeah, sorry, I given for granted, but this is a very. I cannot write and speak about different things. Degrees of freedom. Actually, this is. It's a very important acronym that I'm going to use a lot. So for who of you that is not familiar with kinematics or very basic concept of robotics, degree of freedom is related to the capability of, in this case, a node, but of course we can make also other examples, and the capability of defining a node through a specific parameter. So we will see a lot of examples of this, but in our specific case, a node is defining an element, right? Like the example that we saw here. So this is an element that is defined by two nodes, 1 and 2. We can have one node, so for example, node number 1, with several degrees of freedom. What are the degrees of freedom related to node 1? Maybe, for example, the displacement on the upside, so following y direction, or the displacement through the x direction, or the displacement through the z direction, but also rotations. Node 1 could also rotate so that, of course, the rest of the system should be rearranged accordingly, rotate along z-axis, along the x-axis, and along the y-axis. In general, this is something that I can anticipate from a lesson that I actually would have given later on. In this kind of software, but in general, in this kind of problems, for each node, there are generally 6 degrees of freedoms that are associated to them. In this simplified problem that we are going to see now, the most of the times we are going to restrict the problems with 1 or 2 degrees of freedom for each node. But we will see that it is very important to keep in mind that actually, especially when you're going to use the software, for each node, there are potentially 6 degrees of freedom associated to them. Okay? So from now on, when I speak about degrees of freedom or DOFs, I'm relating to this concept. So now let's go to another example. That is the example that I mentioned before, actually. So we are going to see how we can solve a relatively simple problem with a mathematical approach, with an analytical approach, sorry, with an exact solution, and with a finite element method. And we're going to see how the approximation of the finite element method, of course, can be acceptable or not, depending on what you are, what are your requirements from this point of view. So let's consider the case of a tuppered structure like this, like the one that we saw before, where we have a force, and in this case is applied longitudinally like this. We have the x-axis and also the displacement that is related to x in this direction. We have the length of the bar, it is like this, LT. We have an initial area, so for x equal to 0, that is also different since it is tuppered with respect to the final area that is smaller. And we also consider to have, and this is the, say, the difference that we are going to consider. From an analytical point of view, as I said, the model is defined, can be approached considering infinitesimal sections of the system, right? So let's consider a very small part of the problem, the x, and also its infinitesimal displacement. Okay, this is just to define all the letters that we are going to use. Okay, so you may recall from the mechanics of materials that there is a very well-known equation that can be used to solve this kind of problems, or at least that can relate the force applied to the deflection that is usually experienced by a system like this. So this is something that you may be familiar with. Of course, it comes directly from the constitutive equation of materials. Maybe this is one equation that you are familiar with. Of course, if you express the stress like the force on the area, you have this, and if you express the strain, this is something that you know, right? Yes, no, yes, yes.
Yes.
Yes, sir.
Good. This is the stress, the strain, and the elastic modulus of the material. This is the constitutive equation of materials. You can express the stress like the force on the area. Elastic modulus remains the same. The strain can be defined as, in this case, using the same symbols, the deformation on the initial length. Okay, so if you rearrange this equation, this is how you can obtain the one that I put here. So nothing really new. This is something that you already know. And comes directly. Yes?
Which is the difference between delta and epsilon?
Delta and
Epsilon.
delta. Okay, so delta is the deflection, so it's the deformation. So in a way, you can consider delta like the final length minus the initial length. In this case, where you are going to elongate the structure. Epsilon is actually this quantity, but normalized with respect to the initial length. This is, by definition, this is delta, and this entire ratio instead is the strain epsilon.
Okay, thank you very much.
Okay. Then actually, for your knowledge, there is also another parameter that we are not going to use, but the stretch that is actually very much used when you are dealing with hyperelastic materials. That is L final. Sorry, this is not exactly L on L initial. But again, we are not going to use it. So it's just for your knowledge. Okay. So let's remain with delta and epsilon, strain and deflection. So now we know how this equation is where it comes from. And then we can also compute the exact solution of our problem, considering the differential element area that we defined here. So we have delta again, that is, let me write it, L A E. The U, that is the deformation, the infinitesimal deformation, as we said before, that is the infinitesimal representation of the deflection, is equal to F dx, that is the length of the infinitesimal element that we find, on A, that, by the way, is not constant because it varies along x, right? From A0 to AF. So we should consider it as a function of x multiplied by E. If you want to visualize it even differently, it may be more useful. You have that the area is actually starting from A0. I pretend to be, I mean, it should be a line. And AF. Of course, on x equal to AF, we are at LT, that is the length of our tapered bar. Right? So it's just another way to represent of the area with respect to x. Okay? So looking at this, we can also write the dependency of A with respect to x this way. AX equal to A0 minus A0 minus AF, which multiplies x on LT. Okay, this is something that if you would like, you can demonstrate yourself. It's an easy calculation. And also, if we define, just for convenience, another parameter, alpha, as the ratio between AF minus A0 on A0, we have that AX can be rewritten as A0, which multiplies 1 plus alpha X on LT. Okay? Now, if we substitute this last definition of AX into the differential equation that we wrote here up, and we if we integrate this equation, so if we use this and this, and we also and if we integrate, we have Ux is equal to F LP on E A0 alpha logarithm of 1 plus alpha X on LP. So this is the, let's say, description, the definition of the distribution of the displacement, which depends on X. So this is the kind of, an example of field problem that I mentioned before. So this is the description of a distribution of displacement on a system. Our system, in this case, is the tapered beam, the tapered bar. Yeah, maybe before going to the stresses, I can also, since there was also the question related to the deformation, to the strain, we can also make an example to clarify once for all what is the difference between position, displacement, and deformation, or at least what are the kind of symbols that we are using for all of those. So consider one element like this, where you have node 1 and node 2. Okay, and then after deformation, this is, let's say, this is an element of a more complex system. We are just studying that in space. So this is the definition, one element in space. At the end of our analysis, this element is actually like this, maybe even more. Tends to be a linear line, this one. So this one is the displacement of node 1, right? This one is the displacement of node 2. So U1 is defining the value of the displacement. Of course, U1 is equal to the different coordinate. So you have the coordinate of node 1, and you have the coordinate of node 1 after the deformation. The difference between the two positions, so the two coordinates, gives you the displacement, that is U. And this is U1. For U2, of course, it holds the same. So if you have the two positions of point 2, so x2 before and x2 after the deformation, you have the difference between these two coordinates gives you the displacement, u2. Once you have the displacement of each node that is composing the element, you can compute also the deformation. And the deformation is simply the difference between the displacements. Okay? Now, going back to U, so the definition, well, the distribution of the displacement with respect to x, we can also use the Hooke's law to define the stresses. Let's recall sigma x elastic modulus multiplied by the strain. But we also know that actually the strain, as we said, is the delta U that, of course, when we speak about differential equations, is the first derivative, right, of the displacement. So to pass from the displacement to the strains, we just need to differentiate if we are speaking about infinitesimal, in terms of differential equations. So E multiplied by U first x. Now, this is a very peculiar, if you like, notation that is often used when we deal with finite element analysis. This is a sort of comma, actually. I said one, but this is a sort of comma. When you see this subscript u, comma, x, this means the first derivative of u with respect to x. So maybe I can write it here. U, comma, x actually means du on dx. It's a notation that is used to make a contract version of the notation. Okay? But we know how u is defined, right? We just computed it. So we just need to derive it. But this is actually the inverse of what we just did, right? We integrated to come here, so we just need to go back to find the first derivative of this, so that in the end, our solution is just this. Okay? Questions? These are actually the two, the two equations we were interested in. Field problem is, the aim of field problem is to find the distribution of the of quantities, mechanical quantities in this case. And in particular, we found the distribution of U and distribution of sigma, so displacement and stresses, with respect to X, since we are dealing with a 1D bar element problem. Okay? Questions? Yes. Correct. And this is also clear here. Sorry? It is dimensional. Delta U is dimensional. So only epsilon is adimensional because it is normalized. Delta U. Delta U. Yes.
So delta the epsilon in the bottom is dimensional, no? Delta U.
I didn't get, sorry.
The epsilon you wrote in the bottom as delta U is dimensional. Shouldn't be it divided by X.
I think I lost you. Maybe if I got correctly, you are speaking about this.
Yes.
I guess you said that if delta U is dimensional, but epsilon is adimensional, there's something that doesn't work in the equation.
Yeah, exactly. Actually, this is a good question because I noticed that this actually is not epsilon, but it is delta. So you are perfectly right. And thank you for noticing. This was also maybe your question, right? Okay.
Hi.
Great.
Yes, thank you.
Great, guys. Thank you. This is also confirming that you are with me. Good. Other questions? Okay, let's go and try to complicate a little bit things so that now we again have monodimensional problem, but with more elements. So we have one element here that is now connected to another element here that is again connected to another element. So, yeah. Okay, so what is it about? So far, now I don't know. Yeah, I hope, yeah, I have this other, the previous slide is still there. So this is the problem that we are facing, okay? So this tapered bar that has a force on a side. This is the approach where we are solving the problem analytically with an exact solution. Let's try to solve the problem with a finite element method. So with an approach that is with an approach that is approximated through a numerical approach. So instead of having this tapered structure, now we have the definition of the problem. Maybe I can, before doing this, I can draw the problem again like this. So instead of having the tapered structure, now we have a simplified version where we have the description of the system like this. So we have node 1, node 2, node 3, node 4, element 1, element 2, and element 3. We have, well, in this case, the displacement of S, I'm sorry, of the nodes like this. And all the nodes, sorry, all the elements, just for simplification, they all have the same length. Of course, the 3L is equal to LT. So the total, I mean, the sum of these 3L is equal to the original length of the tapered structure. Okay? And of course, there is the force applied here. Now, let's try to approach this simplified problem with the finite element method. And we can identify for the 3 elements a specific K that now, of course, is specific for each element. So we have K1, K2, and K3. Well, in general, what we should do is to consider that the 3 elements, sorry if I rewrite it, but it is too close to the left side. There is a resistant force here on the first node, and the force, the real force that we are considering, that is applied on the 4th node along the x-axis. Well, we can write, similarly with respect to what we did before with the single element, the equilibrium on each node. So we are going to have 4 equations describing the equilibrium node by node. So we have, I'm not going to divide it graphically, but it's the same procedure that we did before for the single element. So minus R1 plus K1 U2 minus U1 equal to 0 minus K1 U2 minus U1 plus K2 U3 minus U2 equal to 0 for the equilibriums minus K2 U3 minus U2 plus K3 U4 minus U3 equal to 0. And finally, minus K3 U4 minus U3 plus F equal to 0. Okay? As we did before, we can rewrite it in matrix form so that we have K1 minus K1 minus K1 plus K2. This passage should be quite trivial, so I'm not going to explain all the details here, right? This is the same procedure we did before for the single element again. Minus K3, 0, 0. Minus K3, K3. This is multiplying the vector of nodal displacements, U1, U2, U3, U4, and this is equal to the vector of nodal forces. In this case is, minus 1, 0, 0, F. In a more, say, contracted way, we can also refer to these three, the matrix and the two vectors this way. This is K, capital letter K, the vector D, and capital letter R. K is the global stiffness matrix. That is actually also with the notation different, because K with lowercase letters is for one single element, stiffness matrix. When K is in capital letter, it usually refers to the global stiffness matrix of a system that is made of more than one element. Okay? D again is the vector of nodal displacement, and R is the nodal load vector. Okay, let's have a short break, 10 minutes or so, and then we will start back from here. Any questions for the break?
Professor,
Yes.
for the third matrix,
Yeah.
were you calling it I earlier?
The
With
first,
R1, 0, 0, and F.
yeah.
Why were you calling it I?
I. This is, and this is different with respect to the minus R that we defined before. And I will explain why after the break, if this is your question.
Okay, thank you.
Okay, great. Other question?
Professor,
Yes.
D is the vector of nodal displacement?
Yes, it is.
Okay, thank you very much.
Okay, let's have a break.
Professor,
Yes.
I
can hear you.
hear me? Ah, okay.
Yes.
So the vector of nodal displacement could become a matrix or a tensor if we have more degrees of freedom.
Well, no, actually, that vector will remain the same. If you have more degrees of freedom, you increase the number of rows, actually. We will see other examples where, for example, we will add degrees of freedom in other directions and also rotations. But this is usually something that is going to increase the dimension of the vector, but it doesn't become a matrix.
Okay, thanks.
Yes? I cannot hear you, actually. Can you speak loud? Yes. Okay, so in general, that vector is the vector of degrees of freedom because in general, we can also speak about other variables, okay? In our specific case, since we are dealing with displacement, the degrees of freedom that we are dealing with are displacement. So that's why the two things are the same in this case. So in general, we can refer to the vector of degrees of freedom. In this specific case, the degrees of freedom are displacements, so it is the vector of the nodal displacement. So the difference is between K and K. So the first one is the element stiffness matrix. The second one, the second one is the global stiffness matrix. So K is considering all the stiffnesses related to the degrees of freedom of the nodes related to that element. K, but only one element. K, capital letter, is usually the assembly, we are going to deal with assembly later on, of all the stiffness matrices of the single elements. So in a way, K in capital letter is considering and collecting all the contribution for all the single K lower cases that are the stiffness matrix of the element. Okay. 10 minutes. What do you mean? Per gli ingegneri, magari dover guardare che poi c'è Cioè, se ti manca qualche base, che ne so, su questo che matematica non credo, però insomma, appunto su queste costitutive, di solito è questo, quello non c'è problema. No? Se dopo che c'è un po' sbattuto la testa trovi ancora difficoltà, sì. Ok. Allora praticamente era la stessa cosa. I debiti. Sì. Chi sono? Quali? Mi ricordo come non Ah, vabbè. E sì, loro sono queste cose che proprio le cose di materia, questa è costruttiva di che vale come legge universale, quindi per quello che è costruttivo. Non dipende neanche dalla geometria, ma dipende soltanto dalle proprietà del materiale. Tu hai qualsiasi che ha una certa superficie, tu gli applichi una forza, però una forza distribuita. Quello che succede è che tu applichi una forza su okay? Quello che succede è che la sua deformazione, quindi questa è la sua forma iniziale, questa invece è la sua forma, diciamo, sarà schiacciata, no? La sua deformata in realtà dipende dal modulo elastico del materiale e ovviamente per definirla poi ci serve epsilon in questo caso è, se questa è la lunghezza iniziale, questa qui invece è la lunghezza iniziale, qui lo strain è definito come lunghezza iniziale, e quindi questo ti dice che una forza applicata a una certa area determina questa deformazione, diciamo, dipendentemente da quale è la sua elastico. Il modello elastico è una qualità, una proprietà del materiale che è indipendente dalla geometria. Sì, tipo se tu puoi cercare il modello elastico del legno, il modello elastico del vetro, della ceramica, dell'elastomero, e quelli sono proprio numeri proprio che si possono testare fuori. L'unità di misura è in megapascal, ma proprio questa è dimensionale. Questa è una forza su un'area, quindi è una tensione che vorrebbe megapascal. Di solito avremo a che fare con diagrammi di sforzo di formazione per i materiali lineari che ovviamente la linea, quando invece abbiamo a che fare con dei materiali che non sono lineari, si parla o di secante o di modello elastico secante oppure di modello elastico puntuale che va a essere regolare. Questo è proprio un bignami in 2 minuti, però vabbè, insomma, quando affronterai con So, are you there on Teams?
Yes, sir.
Okay. So I noticed that there was a question that remained unanswered from the beginning, actually, and you can probably read the question as well here. Yes, actually, the simplification I made in the very first part of the class today is very, say, it's very visible, right? I really neglected very big parts of the model, and I did it on purpose because I wanted to stress the fact that whenever we are going to reproduce the geometry of a real system on a software or on a, on a model, it will always be an approximation of it. Because, for example, I neglected very big features. But, for example, when you have a real part, a real system, you usually don't care too much about small features that are there because of the manufacturing process, for example. But when the system is going to be used in reality, those features may have, may make the difference. So whenever you go for a model, whatever is a mathematical analytical model or an FEM model, it is a simplification of reality. No way, it's always a simplification. There is always something that is different with respect to reality. The case that I did, it was, a representation that is very rough. But even if you are going to deal with a much more detailed model, it always be a model of the reality. So even if you are going to use a very fine geometry and mesh, you didn't mention, the mesh that you probably know what is it. So if you use a very fine mesh, you still need to validate your model, because it may be that the representation that you use also in your model is still far from the reality because of the kind of interaction the system has with the environment in the real use. Okay? I don't know, Tamerlan, I don't know if I answered your question.
Yes, thank you.
Okay, let's go ahead. Okay, so this is, I just reported here the equation that we reached in the previous slide, say. Now, actually, what we would like to do, since if you remember, our aim in the field problem is to find the distribution of the property that we are studying, right? In this case, the vector of displacement, general of the degrees of freedom, in this case of the displacement. So, in order to do so, mathematically, what we should do is to find P by inverting K, right, multiplied by R. This is matrix calculation. But actually, if you look at the matrix itself, this is the K, the global stiffness matrix. If you give a look at it, actually it is singular, isn't it? Because you can, if you sum all the rows, actually you obtain 0. So, in principle, this cannot be done. So you cannot invert the singular matrix. This should be a very well-known property of matrices. Why this happens? Because actually, if we go back to the model that we used, we actually didn't fix the entire system in any way. So, of course, we considered everything, but the model is free to move everywhere. That's why the matrix is singular, because we didn't fix any display. We didn't put any hard constraint on the motion of the nodes. So here we studied the system, everything is correct, but the solution is undefined, because the entire system can, we can study with this equation what happens to the system, but what happens happen in any point in space, because we don't have any, let's say, absolute position given by a fixed constraint. In order to let's say to solve the issue and to obtain a solution, we can consider that at the very beginning here, so applied to node 1, there is another element I'm not going to replicate it all. Another element that actually has a very high difference, extremely high. For example, just to be clear, let's consider K big. That is 6 times higher than the maximum between all the K's that we are considering. Okay? So now this means that actually we have now a definition for R1. So what we considered before as this R1 now can be defined as K big multiplied by U1. Okay. Now, if we substitute this new equation, definition of R1, into this system, we now have a different kind of matrices. Okay, and without, okay, I can directly write the matrix instead of writing the system. And now we have here K1 plus K big minus K1 minus K1 2 minus 2 2 3 3 This is the new stiffness matrix, global stiffness matrix, with the modified model. Okay, so let me call it K modified. We always have 1, 2, 3, and 4. Equal to, now there is also another modifications, of course, because here, instead of having R1, we have 0, 0, 0. Yeah. So this is our vector of displacement. And this is our, let's call it like this, force of the modified model. Now, you can easily notice that now this matrix is not singular anymore, because we have now this KB. It's preventing to be singular. And we can compute E Yes?
So K is basically position, right?
Yeah, exactly. It is a way to represent a constraint that is not exactly a fixed constraint, but almost, because K is so much big that in the end it is preventing the node 1 to move. Okay? Yeah, in a way, this is the mathematical trick to represent that. So we can now invert K modified to compute our vector of nodal displacement. Sorry, this is no, of course. And now we can go back to the original system, now that we have D, also to compute R that is also taking in consideration the reaction force. No, but I mean, now we can go back to this. Isn't it clear? Because actually, what we did is just substituting this, okay? The only difference between this equation and this other equation is just that we described R1 like K big multiplied by U1, okay? And this is the mathematical trick again to have the possibility to invert the matrix. Okay, so we are always dealing with the same system, but we defined R so that in a way, we are also introducing the possibility to have a fixed constraint somewhere. Okay. Cannot see you, so okay. Okay. It's for you. Okay, good. Okay, so let's, for a second, let's go back to the matrices. I said at a certain point that K in capital letter is the global stiffness matrix, okay? But let's see a little bit more in detail what is the meaning of this. And this is also, let me start with a question that I don't remember who asked about the difference between R, capital letter, R in lowercase letter, and F. So, in general, R is the sum of two contributions. Okay. So, R, again, is the sum of the two contributions. F, that is representing the loads applied externally, and the reaction forces directly applied to the nodes. Loads and reaction forces on nodes. RE are also nodal loads, but they are due to thermal expansion and also on distributed element loading. Distributed. Now, we have that the sum for all the elements for E, that goes from 1 to n, that is the number of elements, of R E plus the sum, again, for all the elements from 1 to n, R E I plus F should be equal to 0, enforcing the equilibrium of forces of all nodal forces. And since we know that, or at least we saw before, that R is equal to minus K, sorry, this is a matrix, multiplied by the nodal load for each single element, we can substitute this definition here, and we can substitute, rearranging F here to obtain 9. That is actually the equation that we saw before, actually this one. And let me write it here. Okay, we can, yeah, for each element. So in this case, we have the global, because we are summing all the elements contribution, K, T, equal to R. So this is, of course, enforced by the equilibrium of force. Okay? This should also, in a way, clarify the use of R, capital letters, small, lowercase letters, R, E, and F. This is, should be clear that in a way we are summing the contribution of all the elements, right? And this can be, this is exactly what is done also to define our global stiffness matrix. So K, as the global stiffness matrix, is actually, oops. I finished my, maybe I still need it up anyway. So, K capital letter K, so the global stiffness matrix, can be seen as the sum of all the Ki. So all the contributions.
Professor, we can see the screen.
Oh, I'm sorry. Now?
Yes.
Okay, great. So as I was saying, the global stiffness matrix, the global stiffness matrix is the sum of the contribution of the element stiffness matrices, some of them for n elements. This sum, technically speaking, is called assembly. So the assembly of the global stiffness matrix is the procedure of summing the contribution of the local, of the element stiffness matrices. We will, I mean, the word assembly of the global stiffness matrix is quite important because this is one of the words that you will see more in errors given by the software itself. So if you make some mistakes in setting the software, it will complain by displaying errors probably related to the assembly of the global stiffness matrix. And you now know that the assembly is the procedure the software is dealing with to sum the contribution of all the elements of your system. Right? So let's give an example of this assembly. We have
Professor?
yes.
Isn't it IJ because K is like two-dimensional matrix?
Well, actually, N is for the elements. So,
okay,
yeah.
understood.
So it's just summing up the Ks that are for the single elements. So this one, of course, is a matrix that can be 2 by 2, or I mean, it depends on the number of degrees of freedom that you are considering for I mean, the element itself. So the nodes that are in that element. But then you are summing all the single elements. So it's I because you are. I mean, we are considering n elements. So let's see in detail what does it mean. So what it means. So this is, for example, the first element with K1. So for simplicity, just let's assume that the displacement are all equal to 1. And let's quickly see what happens to this system and how the matrix, the global stiffness matrix can be the result of the assembly of the local stiffness matrices, so by summing their contribution. So we have node 1. So here, since the displacement is unit value, we can write K1, right? And this is for node 1. Let's consider it also for node 2. We have K1. F2, and for node 3 we have simply this is for element 1. The same analysis can be done for the second element, where Actually, the node 1 is not considered because we are considering the second element. Node 2 is F2 connected to node 2. K2 and K2. With F3. Okay, so this is of course for element 2. So I'm just analyzing the two elements, decomposing node by node, as we did for the first example. Of course, analyzing element 1, node 3 is not considered, so we have these two decompositions. And for element 2, node 1 is not considered because it is outside, it's not connected to the nodes of element 1, element 2, sorry. So we know, I mean, by considering the two elements, we can derive, as we did for the very first example, the local, I mean, the element stiffness matrix for element 1, that as we saw in the very first example is K1 minus K1 minus K1 K1. And then, of course, there are some zeros because these zeros comes from the fact that node number 3 is not connected. I mean, is not part of element 1. And we can sum up with the element stiffness matrix of element 2, that on the other side has zeros that are due to the presence of node 1, that is, by the way, not part of element 2, and then K2 minus K2 minus K2 and K2. Summing up these two matrices, we have K1 minus K1 minus K1, K1 plus K2, 0, minus K2, 0, minus K2, and K2. Okay, so this is actually K for element 1. This is K for element 2. And this is the global stiffness matrix as the result of the sum of the single element stiffness matrices. Okay? And this procedure of summing up, again, is the assembly. So when we're dealing with the assembly of the global stiffness matrix, this is the process that you are dealing with. We can also, let's say, derive sort of general rule to assembly the global stiffness matrices. The global stiffness matrix is only one. And in doing so, there is also this technique that can simplify things instead of doing all the passages that we saw. We can construct a sort of table where we describe the element that we are dealing with and the nodes that are defining the elements. So in this example, of course, the table can be, I mean, as long as you like. In this example, we are considering a system like this. Let me really do it very roughly. With 3 elements, 1, 2, 3, and the nodes 1, 2, 3, and 4, right? So how can I very quickly do the global stiffness matrix instead of going through all the passages. But well, there is, I mean, let's say a thumb of rule of thumb, sorry, that you can use, that is that if you build if you report in a way all the indices of the position that you have in the matrix, like this, and so on. And of course, there are other 8 elements. So you can notice that actually the stiffness values K1, K2, and K3, also looking at, I mean, the shape of our of the example that we saw before, they appear in the stiffness matrix in row and column numbers matching the node numbers in the table. So this means that K1 will be for sure here, and also here, and also here. Sorry, yeah, so the K1 that is defining the stiffness of element 1 has nodes 1 and 2, so it is going to appear when 1 and 2 are going to define the rows and the columns of the matrix. So if you have nodes 1 and 2, you take into consideration the first column and the second column, the first row and the second row. Of course, the intersection are the first 4, right? The first 4 elements. And in those 4 elements, you should have K1. Okay? For the second case, you have K2, that is for element 2. It has nodes 2 and 3. You take the second column, the third column, intersecting the second row and the third row. And what is the intersection? The intersection is these 4 elements. Now, of course, I didn't write it, but here there is 3, 2, 2, 3, and 3, 3. In these 4 elements, you should have K3. In fact, if you looking back at the previous case, K1 is appearing here, 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 because the element that is defining K1 has nodes 1 and 2. So you take column 1, column 2, intersecting column 1, row 1 and row 2, and so these 4 elements should have a K1. Now, negative or positive? For this, there is another rule. When it is in the diagonal, you always have a positive K. When you are out of the diagonal, you have a negative K. Very simple. So first, you have to locate where your K are, and then if you are in the diagonal, you put it in positive. If you are out of the diagonal, you have a negative value. And you can see that here, the example is exactly following this rule. Is it clear? Maybe it's not very intuitive, but this is very simplifying the entire process. Because you just need to know what are the nodes that are defining your element, and with this, identifying the right columns and rows and the intersection of those, you can identify where your K for that element should appear in the global stiffness matrix. Okay. So if
Professor?
Yes.
Could you please repeat the part in which you explain how to put the plus or the minus, the sign in the coefficient?
Yeah. So
Thank you.
For example, if if you would like to put, starting from element 1, you want to define where your K1 should appear in the matrix, first of all, you should, again, see the nodes that defines the element, 1 and 2. 1 and 2 means that you need your K1 appear in these 4 elements of the matrix. Now, once you identified what are the elements where your K1 should appear, all the elements of the matrix that are in the diagonal will have the K positive. So in this case, 1, 1, and 2, 2. All the elements that are element of the matrix that are outside the diagonal, so 2, 1, and 1, 2, will have a negative K. And just for example, as you can see, both the element stiffness matrices and the global stiffness matrix is following exactly this rule, because all the terms that are in the diagonal are positive, and all the terms that are outside the diagonal are negative. Okay?
No, it's clear. Thank you very much.
Right. Questions? Yes. That's a great question. Actually, this means that your matrix will have other values also here, here, and also here and here, because you are going to have another connection so that it's like you are closing the structure. This is the point. So if also node 1 connected in a way to node 3, it means that there will be another stiffness matrix that is going to be considered for in this part of the matrix, and also in this other part of the matrix. Okay. Other questions? Okay, so before the break, we actually defined or achieved our, the idea, the possibility, it was before the break, the definition of the nodal displacement, so the vector of the nodal displacement, right? So we had, we have, no, let's start with B, right? We had an equation that actually was defining our vector of nodal displacement, right? Now, this is correct. I mean, we now know what is the displacement at nodes. But what if we would like to know also what is happening in the middle of nodes? Well, we can apply and interpolate, actually, the displacement that we know in nodes in equation so that we have a continuous description of the displacement of the system. Okay? So, for example, if we assume that we would like to use this interpolating equation to define the displacement of the entire system, so it's a linear interpolation actually, we can, for example, we can enforce that if S is equal to 0, U is equal to U1, right? So we are imposing the displacement of node 1. If S is equal to L, to the length of our system, then, or at least the element that we are considering, then U should be equal to U2. These are sort of boundary conditions. Okay, when, I mean, for S, so the coordinate axis is equal to 0, U, the displacement is equal to 1. for S equal to L, so at the end of the system, the displacement should be equal to U2. We are applying the two boundary conditions. Then, if we substitute this knowledge in the general equation, we have that U1 is then equal to A1, and U2 is equal to A1 plus A2L. That yields to A2 equal to U2 minus U1 divided by L. Okay, now we can substitute the knowledge of A1 and, the definition of A1 and A2, and we have that for the element defined by the nodes 1 and 2, displacement, depending on S, because now all this effort is to have a continuous description, right? So depending on S is equal to 1 minus S and L multiplied by U1 plus S and L multiplied by U2. I just substituted A1 and A2 inside this equation. Of course, well, we did an example with 3 elements before, so the same kind of approach can be used for the other elements, and you will have the same form of the equation also for the other elements. And you can also write this equation again in matrix form, so that you have 1 minus SL and SL that multiplies the vector of nodal displacement. Again, this can be done for all the other elements, but just take into consideration, well, let's consider the calculation done also for the other elements, and we can also obtain the stresses. This is the description of the displacement, right? We can do a similar reasoning also for the stresses, but as we saw before, it is just the definition of the the positive equation. We have the elastic modulus and the strain, and by differentiating the strain, we have U1 next. We have E delta X and delta U squared is equal to U2 minus U1. The same for U2, 3, sigma 2, 3, and for sigma 3, 4, where you have E, U3 minus U2, E, U4 minus U3 and L. So, now, we have all the elements to compare the analytical solution that we found at the beginning and the FEM approach that we found now. Let's see I can also rewrite all the equations here if you like, just for your reference. We have, I will try to do it quickly, the analytical solution for the displacement And we also have the FEM approach. This is to define all the elements. I mean, a generalized description for all the elements. Nothing new. I'm just copying from what we already wrote before, but of course, I don't have all these details here. And for the analytical approach, the distribution of the stress. And here for the FEM approach, again, so let's make a sort of plot. This is really something that I really will try, but I'm quite sure I will not be so successful in doing it precisely. So we have sigma here and x. And here we can have this placement. So this is the most difficult part. This is what we have from the analytical model. So you can see that is a continuous equation that is actually in logarithmic form, but we also have the approximated solution that is given by the FEM approach that is a linearized solution, right? It is composed of segments that are long L. I mean, they have L length. Okay, let's pretend that these are lines. So the solid lines are the visualization of the FM approach. The dotted lines is the exact solution, analytically driven, analytically, I mean, solved. For the stresses, we have a similar approach. We have a maximum that is the force on AF, and the force on A0, so initial and final area. In this case, we have okay. So again, the FEM and the exact solution. The FM in this case is as you see, is a constant. It's constant, right? It's not depending on S, on X or whatever you like. It's the X, the longitudinal proper coordinate. So it means that actually it is going on steps. So there are sort of steps between all the stresses that are calculated by the FEM. So we will see that there are some other more advanced tools to avoid this, but with the basic concept of the finite element method, this is the level of approximation you can have in a field problem on stresses and displacements and deformations. So in the displacement, you have the linear, means the exact one. There is a logarithmic form, and it can be approximated through segments. And on the stresses, the approximation is even, let's say, a little bit worse because there are the steps that are the average of the parts of the exact solution that are considered. Okay, questions? Good. Okay, you and I have another short break, maybe. If there are no other questions, because it's 6:30.
Yeah.
Is it okay? Okay, let's have no more than 10 minutes break. Okay. No, allora, cosa di questo? Cioè, nel corso di ingegneria, questo no, c'è l'approccio FEM. Sì, questo è esattamente. Cioè, quindi, diciamo, anche registrare, vedere i miei appunti, va bene tutto, ma lì, cioè, quel testo di riferimento è esattamente sono i primi 3 capitoli del libro che non vi ho ancora condiviso le slide, ma lo farò appena riesco a sistemare l'area dove di solito. E poi se avete problemi a trovarlo, il libro magari lo dico, però se studiate quei primi 3 capitoli, in questo caso meglio del libro di riferimento. Poi per il resto del materiale del corso, dove non ci sono riferimenti particolarmente precisi, perché sono più articoli, cose un po' più di frontiera, se avete problemi ne parliamo insieme. Su questo invece, poi, ovviamente di nuovo ci sono problemi, ne parliamo comunque, però il libro è stato didatticamente. Quella è una scelta mia in realtà, nel senso che SolidWorks, allora ANSYS è uno dei software più utilizzati al mondo e magari se poi in giornata ne parliamo più approfonditamente. In
Sì, so
realtà,
che si usa anche per la fluida dinamica.
sì,
no?
sì, il discorso è proprio questo, che fino a 10 anni fa quello che vi spiegherò nel resto del corso, anzi si conosceva veramente bene. Nel senso che noi adesso visto le basi informatiche, poi in un paio di lezioni vedremo ANSYS utilizzato in maniera lineare, però a me quello che interessa è l'analisi di materiali soft e analisi non lineare. Quindi mi scuserete, ma io dovrò galoppare praticamente su analisi lineare per andare sul non lineare. ANSYS negli ultimi anni ha fatto un incredibile passo avanti sull'analisi lineare, sorpassando quelli che fino a 5-6 anni fa erano i suoi principali competitor nell'analisi lineare, cioè Abacus, Marknetat e altri, Thomson non è mai stato da parte di queste cose. Insomma, tutti quelli che facevano analisi strutturali non lineari. Visto che ANSYS ha cominciato appunto a funzionare molto bene anche dal punto di vista e è sempre stato uno dei standard dell'analisi strutturale lineare, allora ho pensato che per voi come strumento da poter riprendere anche nella vostra carriera, ANSYS potesse essere completo, per almeno per l'analisi strutturale. Poi se si va sulla dinamica, sull'analisi magnetica, eccetera, appunto a quel punto rientrano anche Thomson, l'analisi semplice, cose. Però diciamo che per questi ragionamenti ho preferito.
Sì,
e poi ti dico anche un'altra cosa molto chiaramente, ANSYS è disponibile online gratuito con una versione che funziona molto bene, quindi dal mio punto di vista è anche un vantaggio per voi da poter gestire la sua lezione.
No, era una questione perché per esempio da anche parlavo di ANSYS, poi ho usato in realtà Star CCM perché era più per la fluidodinamica, perché è un progetto di fluidodinamica, solo che mancavano tutte le componenti di elettromagnetismo.
Infatti.
E per quello, non so, ANSYS è una buona via di mezzo.
Allora, anzi, se lo vedrete, Workbench, l'aviazione Workbench, in realtà ha una marea di modi che potete usare per fare analisi scientifiche. Poi possiamo parlare di interfaccia, se più o meno, possiamo parlare di quanti diciamo, metodi più o meno automatici i vari software adattano per facilitare l'esperienza dell'utente nel trovare le convergenze. Va benissimo, può parlare, però diciamo che secondo me è uno dei pregi se uno può mettersi. Poi appunto c'è anche il CFD, la dinamica, fa analisi di struttura, l'interazione struttura dinamica. Non le guarderemo queste cose, però
per la CFD così a freddo, secondo me cosa è meglio? ANSYS o Star?
Senti, io Star non lo sento parlare ma non l'ho mai analizzato.
Okay.
E in particolare io CFD non l'ho mai fatto. Certo. Sì. Sì. Allora, il discorso è una via di mezzo fra la fisica e la matematica. La matematica ci dice che la materia è singola e tornando alla fisica, effettivamente la matematica ha ragione, nel senso che se noi consideriamo questo sistema, questo in realtà era un problema nostro di base, ma però l'abbiamo studiato in questo modo. Se noi consideriamo questa forza di reazione senza dargli nessuna identità, di fatto non potendo definire R in termini di stiffness, non ci dà nessun termine da considerare nella matrice globale. Se non c'è nessun termine che definisce R, tutto quello che avviene qui avviene come azione e reazione fra gli elementi. Ma questo è sempre vero, ma è sempre vero in qualunque posizione dello spazio. Quindi il problema si definisce indefinito, non è sbagliato, ma è indefinito perché può avvenire in ogni luogo. Okay? Quindi abbiamo bisogno di poter in qualche modo definire R con una rigidezza che però deve poterci dare delle garanzie aggiuntive, che è data dal fatto che la sua costante, la sua definizione è molto più alta rispetto alle altre. A quel punto la matrice ci diventa non singolare, non simmetrica, c'è un certo punto questa carta in più, che matematicamente ci fa capire che è invertibile e fisicamente ci rappresenta questo l'inversione. Sì. Perché una volta che hai invertito la matrice puoi definire D e quando c'hai D puoi tornare a questa per anche trovare R invece che Sì. Non è che vale, cioè nel senso, S è la nostra coordinata spaziale. Perché non posso scrivere X perché sennò è sì, ci sta che da qualche parte io abbia utilizzato X, però quando inizio, non so se ce l'ho ancora qui. Quando ho definito i due problemi, adesso l'avete colta questa cosa, probabilmente non l'ho sottolineata, che avevo messo le S, proprio perché se no si poteva fare. Quindi è un'equazione definita in S come coordinata spaziale. Queste sono le boundary conditions, cioè no, questi sue sono gli analitici, questi sotto sono i due risultati, cioè sono tutte equazioni che abbiamo trovato nella parte iniziale della lezione, però le ho riportate solo per vostra comunità. Però questa U di X e sigma di X sono le due definizioni del displacement e del stress dal punto di vista della soluzione analitica, e questi sotto sono dal punto di vista della. E poi nel grafico l'ho cercato molto malamente di rappresentare. Sì, però i ipotesi ci danno questo. Ah, ma il software dici? Ma che cos'è questo? Ma per scrivere direttamente sullo schermo? Di solito. Però scusa, questo è il computer. No, sì, però c'è abilitato anche dalla questione di poter comunicare con quello. Cioè il mio schermo è touch, però non sono sicuro di poter fare questo. Non so perché la tavoletta è fatta apposta per riconoscere questo. Come? Sì, sicuramente mi darebbe qualche opzione in più, ma di fatto quello che mi dà fastidio è il fatto di scrivere qui e guardare qui quello che sto facendo. Già di mio non scrivo bene, poi in questo modo. Sì. Vabbè, grazie. Perché sto cercando di scrivere lentamente, ma ogni tanto mi parte un po' la mano. Grazie. Si domanda. Okay, we are starting again. Are you there on Teams?
Yes, sir.
Okay, great. Okay, so let's start with a very quick review of what we said so far about the finite element method process. So first of all, what we need to do is to set the model and the elements. Okay, nothing new. It's just what we did all the times that we made an example. We started with setting our model and divided it into elements. Second step is to develop the element stiffness matrix. Third step, we now know what it means. Assemble the global stiffness matrix. Okay. Then we have to define and apply correctly all the loads at nodes. Then we need to apply all the boundary conditions. When I write BC, is boundary conditions. This is an acronym that I will use a lot. Then we can solve for D and R. And finally, we can compute all the gradients. So, for example, the strain that we know, for example, is first derivative on x of the displacement, and also the related quantities. So, for example, we saw examples about the stress that is defined with the constitutive equation. Okay, this is just a recap, very quick recap, just to have a very, let's say, visual also, if you like, recap of the actions, the steps that we followed so far every time we made an example, whatever simple it is, of the application of the finite element method. Okay?
Professor,
Yes?
could you repeat step 4?
Step 4 is the application of the nodal forces, the nodal loads. Of course, this is not a matrix. I don't know if this was the question. So that I have nodes and I am able to make mistakes.
All right, thank you.
Okay. Okay, so now let's make a slightly more difficult example of a 2D beam element. So far we analyzed only bar elements. I will go to the difference between bar and beams in a while. Just me first introduce the aim of this exercise. You may have noticed that actually in the computation of K as the element stiffness matrix, we applied this rule. I'm reading it because the definition is something that you have to take as it is. Then we will discuss about the concepts. So very, very slow. A column of K as the element stiffness matrix, is vector of loads at nodes to give corresponding degree of freedom unit value, while other degrees of freedoms are zero. The first impression of this rule is actually that it is not really not understandable, but I will repeat it so many times and I will explain, say word by word definition. Because actually this is a quite powerful rule that can be used to assemble the stiffness matrix in a very quick way. These kind of rules, probably you will never use it. Okay, let me be very frank. Unless you are going to develop your own codes, it's very hard that you are going to deal with this kind of things. But it is very important to be very familiar to this kind of math, because this is the very essence of the working principle of the finite element. Okay. So that's why.
Professor, we're having some trouble here.
Sorry? I didn't hear you. Can you hear me now?
Yes.
Okay. So I will continue. If there is any other issue, just stop me, okay? So let's try to visualize a little bit better this rule with the example that I mentioned. So let's start. Okay, the 2D beam element is something that we are going to see in a while, but let me recall what we said about the 1D bar element. This is K. This is the very first example that we did. U1, U2, and F2. This is the most general example and the first that we did. We said that the equilibrium is very simple. It's just the equilibrium on the two nodes, U2 minus U1. It's equal to 0. A system with the equation that sets the equilibrium of node 2. Okay, let's notice this. If we set U1 equal to 1 and U2 equal to 0, then we have that F1 is equal to K and F2 is equal to minus K. I don't know if you visualize it. So you have, if you have F1, sorry, E1 equal to 1, it means that the first equation is just F1 equal to K U1, but U1 is equal to 1, so you have F1 equal to K. With the same argument, if you have U2 equal to 0, the second equation leads to F2 equal to minus K U1. But again, is unit value, so it's minus K. Let's notice that we have these two K's, okay, K and minus K. Then let's do the opposite. So if we set U1 equal to 0 and U2 equal to 1, we have that F1 is minus equal to minus K. F2 is equal to K. This comes from the fact that U1, again, as we said before, U1 equal to 0 means that F1 is equal to minus K from here, and U2 equal to 1 means that F2 is equal to K. These are the two application of the two cases, okay? And again, you can notice that now we have these other two differences, okay? This is something that we should be familiar with. If you remember, the solution of this very simple case was that K of the element is equal to K minus K minus K, K. It's not by chance that actually this, the solution that we found here on the top right and the solution that we found here in the middle right is actually the composition of the columns of our element stiffness matrix. So now the definition that I gave you before could be at least slightly more clear. I will repeat. A column of K, so a column of K is vector of loads, this is the vector of loads, at nodes to give corresponding degree of freedom unit value. In our case, the degree of freedom that we gave unit value is U1, it is equal to 1, while other degrees of freedoms are 0. The other degree of freedom is 0. So in order to set the first column or your element stiffness matrix, you can set the first degree of freedom equal to 1 and the other degrees of freedom equal to 0, and your result will be the first column of the element stiffness matrix. The second column of the element stiffness matrix can be achieved by setting 1 the corresponding degree of freedom and 0 all the others. So in this example, the second column is obtained by setting 1 the second degree of freedom and 0 all the others, that in our case is only U1 for simplicity. And the result, so the vector of loads, is exactly what we have in the second column of the element stiffness matrix. So the definition is maybe still a little bit not clear, the most clear, but now you should start maybe also by intuition understanding what is the meaning of setting a degree of freedom equal to 1 while all the other degree of freedoms are set to 0, and the vector of nodal displacement will be the definition of the column of the corresponding column in the element stiffness matrix. Let's make another example, and let's go back to the 2D beam element. That is actually the exercise that I wanted to make. First of all, so what is the difference between a bar and a beam? A bar can be, or at least takes into consideration only axial loads. A beam is instead also taking into consideration bending stiffness. Okay, this is the main difference between the two. Let's consider Let's consider this example. You have node 1, an element like this. It is in this case a beam. In this case, we are also considering some more degrees of freedom. So we have y-axis and the relative degree of freedom that is v, so displacement along y will be called v. So we have this time v1, with this displacement along v. We still have x. We have displacement of node 2 on y. And also, we can also consider moments, since we are dealing with a beam. So rotations of course, around the z-axis on node 1, and rotations about z on node 2. In this analysis, we are considering bending deformations only and the displacement restricted to xy plane, so that we can also apply the very simple and well-known Euler-Bernoulli theory that can simplify at least this exercise. We can see that, of course, all the approximation that we are doing analytically in order to apply Euler-Bernoulli is also, are also applied to the solution that we are going to find with the finite element method. The possibility to use the Euler-Bernoulli theory can simplify a lot the analysis, because we can consider it a cantilever beam with a force applied at the end, cantilever beam with an F applied at the end, and we know very well what are the equations that actually define this kind of behavior, where V max is the deflection B, as we defined as the displacement along Y. Sorry, along Y. V max is equal to F L to the power of 3 on 3 E I. This is, a known equation. I'm not going to derive this equation. And about the rotation, we know that this is defined again through the force applied, L to the power of 2 and 2 multiplied by the elastic modulus, and I, it is the moment of inertia. I'm assuming you all know what is I. If it is not the case, let me know, but we cannot take care of it right now, but probably it will deserve an explanation. Okay. This is about the force. Of course, we have also a set of equations that also define what happens in terms of moments. So the deflection, maximum deflection that you can find in a cantilever beam is defined by the moment applied multiplied by the square of the length on 2 elastic modulus moment of inertia. The maximum rotation, the similar approach, is moment multiplied by the length on E multiplied by E. Okay, this is just the theory of Euler-Bernoulli says this. So this is the set of equations that we can use from an analytical point of view to find our solution. Now, let's consider the first column of K. We are dealing with one single element, okay? So we have only 2 nodes, but in this case, we have some degrees of freedom. Can you spot how many degrees of freedom we are dealing with in this case? And what is the dimension of the stiffness matrix that we are going to have in the end? This is a question also for the people connected on Teams. Number of degrees of freedom and the dimension of the element stiffness matrix. 3 degrees of freedom. Which, can you say the names of the degrees of freedom? Actually,
I think there are.
sorry? So, in this case, we define X, but the degrees of freedom are the one that I indicated here. Because in the Euler-Bernoulli theory, there is not, I mean, this deformation, the shear deformation is not considered. So in this case, we have V1, V2, theta on Z1, and theta Z2. So we have 4 degrees of freedom, 2 degrees of freedom for each node, we can also say. So what is the dimension of the element stiffness matrix that we can expect? Come on, guys. Yeah, correct. So since we have one single node and 4 degrees of, sorry, one single element defined by 2 nodes, each node with 2 degrees of freedom, we have 4 degrees of freedom, and we are expecting to have 4 columns, one for each degree of freedom. And since the stiffness matrices are always square, our stiffness matrix will be 4 by 4. Okay? Okay, so let's start activating one single degree of freedom at a time. So we are going to implement the rule that I said before. I will repeat just for you. A column of K, the element stiffness matrix, is vector of loads at nodes to give corresponding DOF unit value while other degree of freedoms are 0. So if we are going to activate each single degree of freedom and setting them equal to 1 and all the other degree of freedom set to 0, the nodal vector of loads will describe the first, each column of the element stiffness matrix. If we start with the first degree of freedom, it will give the first column. The second degree of freedom will give the second column, and so on and so forth. So let's do it for the first, and then of course it will be repeated for all the others. So let's see the example where the case where we are setting V1 equal to 1. So it is the first degree of freedom. The order of degree of freedoms is usually degree of freedom on X, Y, Z, and then rotation about X, rotation about Y, rotation about Z. So, and this is node by node. I will, if I'm able to do that at the end of this class, I will make an example of an entire matrix with all the ordered degrees of freedom. Okay? Yes. The definition is for also for multiple elements. Yes. We will see. Yeah, the extension. Yeah, I think we can. You will see that at the end of this class, if I'm able to reach the end. Actually, it's quite late. So. Okay. Okay. So V1 equal to 1, and the other degrees of freedom set to 0. So V2 will be equal to 0. The rotation about Z on 1 and Z on 2 will be 0 as well. So if we make this drawing, of course it is not very, sorry for this, I will try. Not bad. So this is V1, it is equal to 1, we said. And all other degrees of freedom, as you can see, are 0, because there is no rotation here on node 1, there is no rotation on node 2, and there's no vertical displacement on node 2. So we just activated, let's say, the degree of freedom related to the vertical translation of node 1. Okay?
Professor, I can't hear anything. The audio is not working. Nope.
Yeah, I think even his camera's gone.
Yeah.
Yeah, I think he disconnected.
Yeah, I
Let's
hope
ask the
it's still
people in the
not
room. Who's in the room?
Yesterday happened the same. At I don't know why at 7 maybe they cut off the Wi-Fi at university. I don't know.
But the registration is still going anyway. So
They will hear us.
Yeah, but that's strange. I mean, the registration is still going because he hasn't, I guess, closed. I don't know. That's very strange. Sarah wrote on the group that he's trying to reconnect, so he is aware of the problem.
Can you hear me?
Yes, sir.
Okay. I'm sorry. I don't know how much you lose lost of my presentation.
About 5 minutes. Maybe 5 minutes.
5 minutes. Check.
Like, just after when you draw the elastic lines.
Okay, so so you got this part. So this is the let's say the elastic line. And we were speaking about how to study that using the equations that we know about the cantilever beam set by the Euler-Bernoulli equations. So we set here the degree of freedom that is, let's say, activated, that is V1 equal to 1. Then we have the moment around node 1, that is K to 1, the stiffness matrix, the stiffness element that is related to the moment is K to 1. We have rotation about node 2, whose moment is K for 1. And then there are all the forces, F, K3, 1, and the other force that is K1, 1. So in doing this, we said that activating V1 equal to 1, we are also setting that the maximum displacement on V, so the deflection of the cantilever beam, is equal to 1, meaning that the contribution of the force and of the moment should be, the sum of them should be equal to 1. So 1 is equal to K11. L3 on 3 EI minus, I'm sorry, I'm really close to the definition of F. I apologize for this. So what are these two terms? This one is the force term. So this one is the force term that you can see here. So it's the term related to node 1, Fk11 divided by L to the power of 3 on 3EI, minus plus the contribution on the moment, that is minus mL squared on 2EI, that is this one. So the moment K to 1 multiplied by L squared on 2EI. And this is what we can set for the displacement. For the rotations, we know that having activated V1, the rotation, the maximum rotation, is equal to 0, because we have to activate 1 by 1 the degrees of freedom. This means that 0 is equal to the two contributions given by the rotation. So again, from the Euler-Bernoulli theory, we have minus K11 on 2EI plus K to 1 L on EI. So solving these two equations, I mean, having a system with these two equations, we can derive the definition of K1 equal to, sorry, K1 equal to 12 EI on L over 3 and K21 equal to 6 EI on L2. Just if you give me other 2 minutes, I will finish this part so that we can then pass to the other module next time. So we have now a definition of K1 and K21. Of course, what you are expecting is that we have to define 4 Ks, right? Because we are defining the first column of the stiffness matrix. Okay. How can I take the other 2 Ks? Well, with the equilibrium of the system. So the equilibrium of forces and the equilibrium on moments. So we know that the sum of the forces on Y should be equal to 0, and we know that the sum of the moment about Z should be 0. From the first one, we know that K11 plus K31 is equal to 0. From the second, we know that K21 plus K41 minus K11L is equal to 0. I don't know if it is clear. So for the forces, of course, it is clear because you just need the 2 forces applied vertically. So this one and this one, their sum should be 0. For the moments, you have the moment K21 plus the moment K41, that should be 0, but also you have to sum the contribution of K11 and the moment that is generated by the force. So it's K11 multiplied by the length of the beam. If you again take advantage of the knowledge of K11 and K21 that have been already calculated, and you have other 2 equations, you have only 2 unknowns, you can derive, I will skip all the mathematical details, you can derive the definition of K31 as minus 12 EI on L over 3 and K41 equal to 6 EI on L squared. Now we have all the 4 elements to set the first column of the stiffness matrix. If you repeat this same procedure, activating one by one the other degrees of freedom, you can calculate one by one all the columns to develop the stiffness matrix of the elements that we are considering. The only other detail that I can give you is that when you are dealing with the activation of the rotation, instead of considering this kind of deformation, of course, for activating V2, this is a symmetric problem, right? But if you activate the moments, so the rotations, what you have to deal with, it's something like this, where you have no displacement vertically, right? Because you are considering 0 in those degrees of freedom. You have no rotation on node 2 because you are considering 0 the rotation about node 2, about Z of node 2, but you are considering 1 the rotation of node 1 about Z. You are activating the rotation. So this degree of freedom, sigma Z1. So in this case, what you are considering is this kind of deformation. So sigma Z1 equal to 1. Of course, when you want to define the last column, you have to activate the rotation about node 2, and what you will have is the symmetric problem of this, right? Okay, so column by column, you can use these elements to define your final stiffness matrix, where you have K11 here, K12, K13. I'm sorry, it's the other way around. It's K21, it's K31, K41, K12, and so on and so forth. So it will be a 4x4 matrix. The procedure that we saw together is defining the first column, activating the rotation about node 1 on Z is defining the second column, activating the vertical displacement of node 2 is defining the third column, and activating the rotation of node 2 about Z is defining the fourth column. Now we repeat for the last time. A column of K is vector of loads at nodes to give corresponding degree of freedom unit value, while other degree of freedoms are 0. Now, I mean, it is, let's say, the fastest way to define this process, but now, I mean, also neglecting the definition itself, the important thing is that you understood what is the mechanism to find and to define column by column a stiffness matrix of an element. Okay, questions? Yes.
One is why K has different dimensions.
Sorry, didn't get. Can you repeat, please?
Maybe I can write.
Okay, yeah, please. If you can write it, it's better. You mean the definition? So you cannot see the question. So someone is asking why sometimes we are using L that is cube, sometimes it's square. Well, can you hear me, Martina? Can you hear me? Yes. Okay. So the idea is actually that these kind of equations are coming directly from the Euler-Bernoulli theory. If you want to see details about how these equations are defined, I can maybe give you some other material, because for this lesson I must give for granted that you should let's say you have to give for granted that those equations are correct. But if you like, I can provide more material on the derivation of the Euler-Bernoulli theory. Okay, sure. Other questions? Okay, so see you next Wednesday in Pontedera. Also for you guys on Teams, see you next Wednesday on Teams. Bye-bye.
Bye, thank you.